And I'm Davide Consoli. So this is an hands-on session, and I did put the link to this presentation on MetroMost if that's convenient for you, or otherwise you can just scan this QR code. I fear I didn't put in a short URL, so now the QR code is quite fine. But yeah, let me know if you have issues in case I can prepare another QR code on the fly. Well, what? Better? Did someone manage to scan the QR code? Does it work? Perfect. Well, the link is to the slideshows, but most important, if you take the presentation and you click on this icon, you should get to this Collab notebook. And if you want to follow actively, I invite you to make a copy of this notebook. So you can go to File, and you can save it as a copy in either Google Drive or GitHub. And if you do that, then you will have the rights to modify it and do your own exercise. Or otherwise, I will follow with you the process. Is anyone going to try to follow? Did you manage to make a copy? Please, in case, raise your hands, or I can just wait a bit. Okay. Someone managed? Thanks. Yeah. So if you made a copy, what I first invite you to do is to start this first cell in which we install this library. It will take a bit, so let it run. And in the meantime, I will introduce a bit the slides to see what we are doing. Okay. Yep. Okay. I assume you started the cell. If not, please raise your hand and I can wait a tiny bit more. Okay, I don't see hands up, so I will start with the presentation. So what I will present is a small example on our typical workflow when we have to do large-scale mapping. And what we work is in a sub-region, but usually we work with global products or at least European scale products. And we work with Landsat data at 30 meters and time series. This translates in terabyte and even sometimes petabyte of maps produced for a single product. And because of that, we need to have a good performance in terms of computing and storage as well. This is a typical setup when we do machine learning, but it's also with small variation. You can also do some process-based model and in general map products at large scale. But let's start with a general case. So we have our data stored, satellite data and other sources of Earth observation data that we store in an S3 implementation, open source, based on SeaweedFS. I assume some of you are also more familiar with AWS or other commercial alternatives. This is an open source implementation that we have in-house, but until you have a S3 interface, this applies in the same way. And we keep our data stored with some other information, substantially in a CSV file or in Excel. And we try to keep the data tidy in the sense that we have them all in cloud-optimized GeoTIFF formats, and we can access them easily with our infrastructure. And then through this, with this data and with other in situ measurements. So for instance, today we will work with a cloud cover dataset, but can be soil data, can be gross primary productivity. It really depends on the application. But let's say we work only with point-based data. So like in this small image that you see here, for this land cover, we have a shrubland in this point. Here it's mixed forest, evergreen forest, and this is point data, while our catalogs here are all raster data. And what we want to do is train a machine learning model substantially to predict what's the land cover, what's the soil properties all over the world or in general in the region of interest. And so we train the model on a point based, and then we do prediction at global scale using the raster data as input. I don't know who is familiar with similar workflows. Is anyone doing something similar in your organization? I see some hands. And yeah, I guess. So for other that are less familiar, this is of course not the only way to proceed, but that's what we do in-house. And indeed, to have something scalable, we also developed a library in-house that is scikit-map. It's a Python library, but Python is mainly at the user interface level, but the backend is mostly written in C++ and interface with PyBind 11. For the machine learning part, we rely a lot on scikit-learn and other models. Also, to scale up, we also do compile some tree-based model with TL2CGen for someone that maybe is familiar. And once the model is trained, we have our data. We want to produce prediction in large scale. To make it parallel and distributed, we work with tile data. Mostly for Landsat, we work with 1 degree by 1 degree tiles, but this is totally dependent on the application and on the data. And we distribute our computing with Slurm, but that's more cluster level, and I don't want to dig much into it, but maybe some of you are more familiar with Dusk, and even though they are not totally comparable, they're often two alternatives for this task. But let's see a bit more in detail what we introduced before. So the Landsat data. So satellite images have a lot of clouds, other atmospheric contaminants, and I mean, they are contaminants, but for some people are the interesting thing. For us, it's not what we are dealing with. So what we do, we mask out the clouds, we mask out also other shadows or other potential source of artifacts for our maps. And because we don't have a value there, we cannot send to most of machine learning algorithm in input not a value. So what we do reconstruction of these images. And this you can check in this publication. Now we did it for Landsat, and we released it open source. And actually, we are going to, so we actually finished the upload on TDSC, Copernicus, Data, Ecos. Okay, the Copernicus, I don't remember, never remember the acronym, but the new Copernicus portal to work with Sentinel and other products. And soon it will be available there, so easier to access. But what we did in this product, we get filled or reconstructed the time series based on images from other years, but with similar seasonality. So you can see here the images that are already in a bi-monthly aggregated time frame still have a lot of gaps. The gray is the no data. And after reconstruction, we have a complete image. The same goes for other products that we often use. And this is a broad topic. There are other ways to do that. And again, we are showing what we usually do in-house. And so these are the main data source that we are going to use for this work. But we also use often, we mix sources of data. So as you will see, I will also include a DTM product bit from MUFON. I don't know if it's here. But we tend to have different products mixed to derive our predictions. And software-wise, again, we rely on our circuit map. It's not the most friendly library, I have to admit. We are working on making it more accessible, but at least with the collab, I hope that you can follow and see it, what you can use also in your workflow. And regarding the data, as anticipated, we work with a land cover, but in general, we try to follow the ETL approach. So we gather different sources of data, we standardize, we drop what's as artifact or it's not relevant, and then we try to harmonize them and put in a standardized way in which we can still find what's the original source, but we can also use different sources of data. And what I will show is limited to California. Otherwise, I cannot really show in Colab already like this, as I will show you later. I had struggles doing predictions, even for one tile. But so in this region, we collected different sources of data. You will have, in the Colab, you have the link to the source. And you can see we have the coordinates, the year in which it was sampled, what's the class in this harmonized framework, and what's the original source of the dataset. And we have 14 classes in this region. And yeah, that's it for the source. Then for the coverage layers preparation is following what I described before. So we start from the cloudy data, we mask out the clouds, we aggregate them temporarily, we reconstruct them, and we organize them in S3 format for cloud optimized upload in a S3 interface. And from those data, we derive indices like NDVI and DWI or other simple indices that we compute on the fly, so we don't double or even more the amount of storage we need to use. And so we work with time series. These are bi-monthly images, but we sometimes, as you will see, also aggregate to yearly products. And then we use the temporal information also for the prediction, or at least for the spatial overlay that I will show there. And we exposed all of our data when they are in a at least published or at least submitted paper. And you can access them through OpenLand Map. In OpenLand Map, we have all global data sets, but we also have Ecodata Cube for European only sources of data. And there is so if you Google it, you will find access to the graphical interface. If you just put stack in front of the URL, like here, you will get access to the stack catalog. I mean, C is already catalog, but just to make it clear. And that's it. The next step I will introduce soon. Well, let me move to the collab for a second. So did anyone manage to install the library? And okay, I see some yes, it's good. And following the cells, we also need this other package to directly get the data from Google Drive. That's faster. And then we can import some packages. And this is essentially what we just saw in the slides. These links connects to the land cover data I described. There is a source. Oh, yes. The global dataset it's already available in Zenodo, and I didn't really work on it, but my colleagues did, and this harmonizes 5 different sources of land cover products, and we keep this information in the output, as you can see, but the data is simply accessible through this Parquet file. And what you add is already cropped to California, so only involves points in that area. So let's just explore a bit the data also in QGIS. Let me pick them. Now, if you downloaded it, you should get in the files this Parquet. Did someone manage? Were there issues with downloading, reading, or did someone manage to get the Parquet file? Okay, I see some yes. I hope it's the case. So this we can just download. And we go to QGIS layer, or we can just drop from downloads. Oh, sorry. I did put the Parquet, but I need the GeoParquet. Sorry. So I wanted to skip this before, and then I forgot to launch. So this will save the data directly in GeoParquet, so also including the geometry information that QGIS can read. And it should be here. Okay, now it's better. So this is a bunch of points. We cannot see much like this, but if we change a bit the symbol and we put some labels, we can get a bit more. Single label, and we want to see, for instance, the class. And let's put some mask, some buffer. And let's see how it looks like. We zoom in a bit. Okay. Okay. I hope you can read a bit, but that's essentially what we have. This is quite dense data set for Vancouver. So you see we have also repeated observations sometimes. And these are the classes, for instance, evergreen, shrublands, and the other 14 that I'm not going to listen now. And here you see in GeoPanda you can explore the data, and that's pretty standard, I guess. Some of you practical with Panda or GeoPanda, or is it something new for you? Let's see. Raise your hand if you don't have experience with Panda or similar.
No, other way around. Raise your hand if you have experience with Panda.
Okay, most of you did. So indeed, you should then follow quite straightforward. And here, I just want to see the set such that these are univoc. These are the sources of the data sets. We have a lot of different versions of glance, dynamic word, global pass-through watch, and word serial. And those are the 14 univoc classes. So we have trees, we have snow, and then we have the original classes before harmonization and the final class. And we can also do some small statistics on the points. So you see that in California, the dominant land cover, at least for this sort of point, is shrublands. Evergreen forest comes second, but indeed, being quite arid area, I guess, shrublands are more dominant. And now that we catched up, at least with this part, we can go a bit deeper in the classification workflow. So space-time overlay. We already anticipated that we use point-based data on raster, but in order to give an input to the model some features that they can train to understand which class belongs to a certain link cover based on the layers that we are going to use as features, we need to do a space-time joint. I don't know if overlay space-time joints are familiar terms for you, but essentially we want to know in this point where we have mixed forests, what's the value of the green band in this specific time. So as you have seen in the training data, one of the columns that we have is the year. Based on the sampling year, we consider only information, so only satellite images that correspond to that year. For instance, this is the green band in 2006, means that we will use this information for the first point, and this is a single cog file. But if instead the sample was observed in 2022, we will use another file. And this workflow is automatized in scikit-map, and we only need to provide a CSV file with proper formatting. I mean, we would like to make it something more standardized and accessible, but for now it's a quite of in-house solution, even though quite flexible. And you can see here an example. So this is the catalog that we are going to consider for this experiment. So you see we have the name of the layer that will be used to describe the feature in the machine learning model. This is the path that can be either a local path or a URL, and with HTTP interface to S3, you can easily access to it. So for instance, this is the blue band. This is the green band, NIR, all the 7 bands from Landsat until the thermal one. And you can see that the temporal solution is bimonthly here. And this is a temporal variable. But we also use some static variables like DTM. And we assume DTM to not vary, so we don't have a time series of it. We have only one layer. And this layer is here. So you can see legend DTM TIFF. And this column, instead of being temporal, is common. This means that the same layer will be used for all the years, differently from the other temporal layers. Is that clear, or? Okay, I see some yes. So indeed, there is not a time frame. We just leave empty this field. And the other interesting part to see a bit here is from these bimonthly row bands, we also derive, as anticipated, other indices like NDVI, NDWI, NDSI, NDTI, SAVI. And to do this on the fly, we created this URL-like interface that we call Whales. And you can see that in this bit long URL, we specify, okay, take the red band as the minus component in a normalized different formula. And so you subtract the red band from the NAR to get NDVI. And we have scalings that depends on how the data is saved. And we can just write this, and Scikit-map will compute on the fly the indices. And this is, again, a bimonthly temp series, so 6 values per month. But maybe we also want to use an aggregated version that is yearly. And this we can do, for instance, taking the percentile. So this is another whale. And we do percentile aggregation. We specify which layers we want to include, so which dates, and which percentile. In this case, percentile 25. Okay? And this is the only input that we need to deliver together with the point sampling to do the space-time overlay. Okay. Let me go back to, no, it's still here. So let me go to the code. Okay, here. Now that we have this CSV file, so this catalog CSV, another small thing we need is the tiling system used for this data. Sometimes we use cogs that are global scale. In that case, we don't need a tiling system, but in case the data is tiled, we also need to know what's the polygon, what's the projection. We need these informations, but that's just a job package attached to it. And okay, let's save this. And you can see if you, I don't know if you did run this, but we can also use JSON to visualize the content of the catalog to have a clearer idea what do we mean with this class that we created. And you can see that these are all different layers. So for instance, for the year 2000, we have the same feature that we have for 2021. So the name stays the same, but it's linked to a different S3 URL. So what changes is that here we have 2000. And if we go a bit below, we have essentially the same link, but with 2001. But for the model, this will be transparent because the feature name is the same. And this data will be stored in a matrix format, so flattening the space dimension and only having one index associated to each layer. Yes, please. Let's maybe with the microphone because I also had some struggles hearing you.
If you had like a predictive interface, say through some web application that you were hoping to let people play with different values of, I don't know, temperature or whatever, would you still want to compute things like NDVI on like on the fly, or would you rather have a TIFF, or is like the storage too big for that, or what's better for sort of fast prediction?
So there is always a trade-off, and if you, for instance, you have this application in which you want to use only NDVI, and you always use NDVI, maybe you want to pre-compute it, but only mainly because otherwise you have to read both the NIR band and a red band. But most likely the bottleneck is not the computation of the NDVI itself, is the I/O. Usually I/O is the slowest thing in just spatial pipelines because a lot of data. So I feel like if the implementation of the NDVI is compiled, it's almost instantaneous. If that's not the case, of course, better to pre-compute, but still better to pre-compute because you read half data. But in general, like in this case, in which we use all bands and we derive a bunch of indices, that's for sure more efficient to just store the single bands. And we tested, and it's actually faster to recompute on the fly than to store the data. So,
and
yeah,
maybe I don't know if you mentioned, but there is a Python library called Awesome Spectral Indices. It has like about 120 indices documented with references. It's kind of just you just pull it, like from a shop, and you have different teams, vegetation, soil, water, I don't know. So you could do all this stuff on the fly. I mean, anything which is linear formula, right? But it's good to do computing engineering. When you start doing a project, do this computing engineering, so you sketch it a bit. How many times you're going to use it, how much storage you have, what's the cost, right? And it's a good to, as soon as you go to big data, you really have to engineer the whole thing. And sometimes the storage can be cheaper option. But in our case, yeah, most of times now it's just on the fly, right?
Yeah, for this kind of application, yes, because we try to use all the bands and different combinations. So instead of storing 100 layers, we store 7.
But let's say if somebody wants to visualize, if you have like 10,000 people, they want to visualize NDVI all around the world, different places. Then I don't know if you want to compute all. I mean, it sounds silly, like computing it over and over. But it could be that spends less electricity. It could be it's actually more ecological, so just to compute than to really save the data.
Yeah, it's really application dependent. But yeah, good question. So now we have this nice catalog. We have our points, and we want to do the spatial joint. So here I did manage to run it in Colab, but I'm not sure it's fast enough for this time. So what I will do, like Rob taught me, is like doing in these cooking programs in which you show the recipe, you start cooking, and then you stop and you show the cake after it's made. So you can just block this computation. And I uploaded the overlaid data on Google Drive. So you can simply download them and we are ready to go. So the overlaid data will substantially be the same point we have for the land cover. We just add a bunch of columns that corresponds to the number of features that we have in the catalog. And so again, in the way we implemented it, we have the same features for different years, only different data. So this means that even if you have 300 layers, but there is a lot of temporal information, what you will have as number of features, it's only the unique features. And we leave in the name the why that corresponds to a general year information. But I don't want to be confusing. I think it's easier if I just show you. So if you open this overlay data, this is what we had already before. And here you can see we have suite 1. So this is suite 1 band. The time frame is from July 1st to August 31. And this is the placeholder for the year that will depend on the way you predict. And another example is here. There is a thermal, all these bands. And overall, this time frame is now 93 columns, while the original training data, it was only 9 columns. So we added 84 columns. And you can see, I mean, the values here are scaled from 0 to 250 because we store the data as integers, but you can interpret it as float from 0 to 1 if you prefer. It should not really change for tree-based models, and it's more interpretation-wise. And this is the DTM instead. You can see I think this is in decimeters, and you see it varies quite a bit. And this is the only information that is not temporal. So you can see that the time frame here doesn't include the why, because it's in common for all the years again. Okay. And now is the model training part. So I will go back to the slides to show a bit. So model preparation. We have plenty of options. We could go for neural network, supervised machine, tree-based models. And we work a lot with random forest or boosted trees, like in this case. And I took a light GBM implementation of gradient boosting decision trees. But again, after you have this data, this is quite flexible. Also, the library prediction-wise, you can simply send what's the prediction functions and keep simple formats that will be only samples by predicted output, and then by general. Again, we use scikit-learn, in this case, not for the model itself, but to do some fine-tuning, so some calibrations and feature selection phase. And I don't know, is some of you familiar with LightGBM? I don't see many hands, but substantially it's just a Microsoft implementation of gradient boosting trees that is also optimized for performance, not only for the is not a classical implementation of the gradient boosting trees. And I hope instead to have some of you did that experiment a bit with scikit-learn. Did you? Maybe for the hackathons? No one used scikit-learn. Oh, I see some hands. Good. Well, if you are familiar with Python and you want to explore machine learning, scikit-learn is a good framework where that includes a lot of models and, in addition, a lot of tools beside the model themselves, and that's very useful. And I mean, there are other alternatives, of course, but this goes beyond like it's not only for 3 models, but that's what we focus on in this case. So I will import a bunch of libraries, and then let's dig a bit in this code. So what we first need to specify is the target feature. So what we want to predict. And in this case is class. So it's simply the column name of the class that we have here. And however, the features that we have, we also want to clean them a bit because some of them has no data values because of availability, and even though our product is get feed, for instance, is also land masked, and some wrong coordinates or simply samples that were in water might impact the training of the model. So we just remove some columns where we have a lot of no data values. And for the rest, we drop. When it's really a small fraction of points, then we just drop them. And we end up with the same number of columns. We didn't drop much. We just drop some points. And we define the features here that will be used for the model. And also what we have to do is to encode the classes that we have. So we cannot straightforwardly send to the model rock outcrops or shrubland. We just associate an integer value to each of them. And this is all sort of pre-processing for the model training. And you can see we also split the dataset in 3 folds. So we have a calibration dataset that will be used to determine the hyperparameters and the architecture of the model. We have a test dataset that we don't touch until the very end, and we all use to check performances. And we have a train dataset. I don't know if you are familiar with machine learning. For you, this would be very trivial. And I will not dig in discussion about cross-validation and other things. It's not really the focus of this topic, but I'm sure if you're in the topic, you know better than me. I just keep it simple. So I use one dataset for calibration, one for training, and one for testing. And yeah, that's what we are left. So for calibration, we will use 3,500 points. And we have a new column that is the encoded class. So you can see our integers from 0 to 13 or 1 to 14. And another important step is the feature elimination, because why is this important? Currently, we have really a lot of features. So, I mean, relatively a lot of features. So we have about 90 features, and we are predicting a very small area with very little classes. And most likely some of the features could also be noisy and degrade a bit the model. So this could lead to artifacts. And even if not, what for sure will lead to is higher computing time because of reading data, because of running the model on more features. So feature elimination is very, very important task. And we just use recursive feature elimination. This is also from scikit-learn, as you can see here, this line over here. And we end up with 30 features that we selected. So again, now I already trained a model, and most likely this selection should be similar or consistent, but since I'm not sure that I did do the seeding properly, I will just use, oops, sorry. I will just use this set of selected features. So we can see what the model chose. And you can notice there are a lot of derived indices. So for instance, it doesn't use the thermal bands at all, even though it has 7 features that are thermal band that was not picked up. But indeed, Landsat thermal band doesn't have a good reputation and might be not relevant for this application. And you can also see that the DTM was picked as feature, and then there are a bunch of other normalized different indices. Some specific MOMs were picked. For instance, you can see a lot of data is taken from July and August. This is probably because these images contains less clouds or less artifacts, and this also makes sense being in the northern hemisphere. Another thing we can observe is that there are also yearly, so like the quantile aggregated information comes up, probably also because it filters out more artifacts. But most likely it's not a very unique solution. Probably if you just drop one of these features and put another one, it won't change much in terms of accuracy. It's really about the quality of the data that you use. And the other calibration phase that we do is the hyperparameter tuning. And gradient boosted trees are quite sensitive to hyperparameters. So this is really important if you use such models. Here we use, so like GBM also has other form of models. So you have to specify what's the boosting type if you want specifically gradient boosted trees. And then you decide the maximum number of estimators. That would be the number of trees equivalent. And what I use here is early stopping. So when the variation in the target loss function is saturating, let's say, it will stop. And even if it doesn't reach up to 1,000 estimators, and hopefully it doesn't. So for the rest is mostly about the gradient descent and derived parameters. And also on the shape and depth of the trees and the residuals. So also this operation might take quite a bit. And for this, I will stop and just go through what I got as output in the previous run.
How long will it take if you have left it running?
Maybe half an hour or 1 hour.
And you don't see the progress, right?
Yeah, you see some
You see progress? Okay.
Yeah, it does different iterations.
Okay.
But yeah, takes.
But it's very dangerous to do some fine tuning that actually doesn't improve accuracy, right? You could be computing for hours and the effect is minor.
Yeah, but that's why you have this in this gradient boosting. You have this early stop.
Okay.
So when the delta is very minimal, it just stops.
Okay.
But yeah, and again, I did run it in Colab, so it's not these relatively small models, so you can easily run it on even your notebook probably. But
do you maybe have a plot of the performance of the hypertuning? The plot that shows like the increase in the.
No, I don't have it.
Okay.
I didn't make it, but it actually, if you run it here, it kind of shows how it varies for each iteration. And yeah, at the end of the process, that's what I got before. So you can see the learning rate, the maximum depth, and most importantly, the number of estimators. That is 1043. And in gradient boosting, this coincides with the number of iterations that would take. So this data we can use as input to train our model. And I take back the data that we created before. So this is so from the data frame for the train, I derive the features and the target variable. Then I just use GBM on this data set, and I use the best parameters that I just got to train the model. And then I test it on the test data set. So let's run. This should be, I didn't click this one. I remember this should be quite fast because this is training only one model. When we do this hyperparameter tuning, it trains a bunch of models and really takes a lot. But this should be relatively fast. Yeah. So you can see here the recap. This is for a single class, but also we have a global performance like the average F1 score. We are around 84%. That's quite good accuracy for such products. And yeah, if you put more effort, this really has limited features, but at the same time is also a small region. So it's quite easy. Of course, if you want to have a model that works at global scale, you really need to do more machine learning digging. And we can just dump the model with joblib, and the model will be used after for predictions. Another thing we might be interested in is just to check also against the training data set to see if the model overfits a bit. And it does a bit, because you see it's a bit higher, it's quite higher. Accuracy is still not 100. So at least F-score is not 1. And that's quite good because these models have the tendency to overfit quite a lot, but this is still acceptable. And then we can also plot a confusion matrix to see what are the criticalities. And you can see, for instance, one big confusion happens between shrublands and evergreen forests. That's quite plausible, and for the rest, it's quite homogeneous, the distribution of the errors. And or also mixed forest against evergreen forests. And yeah, can we have a microphone? Okay, I gave you the microphone. Okay, thanks.
Yeah, thank you. Can you please scroll up?
Yeah.
Why would it be plausible to confuse the shrubland and the evergreen forest?
I mean, I would be more suspicious if I would confuse bare soil with forest. But I mean, the fact that from spectral bands, I observe only green, and I don't have any vegetation height information, for instance. So from remote sensing perspective, it quite could be plausible to have this kind of confusion. And of course, there is also the fact that shrubland is a dominating class. So it's really quite of an unbalanced data set here, and the model is prone to predict more often shrubland probably. But yeah, for instance, if you would have some vegetation height information, probably this confusion could be lower.
Yeah, but you would suspect that the shrubland in the summer, when it's dry, it would have another color than evergreen forest.
Depends. Shrublands can also be evergreen.
But not in California when it's completely dry in summer, I think. But
I really don't know good enough, but let's say that's what we mostly observe from this model. Again, this is not doesn't try to be a universal model.
Okay, of course.
So, but yeah, I mean, I've seen this already in other contexts, and of course, maybe in California is less likely, but I never been there. Yeah.
Thank you. Yeah.
Thanks for your question. Yeah.
Sorry, I wanted to find out how did you deal with the issue of spatial autocorrelation in terms of your points? So there might be points that are in a similar area that may be chosen for the testing, and then that might also overfit your model. How did you deal with that?
Yeah, no, that's a very good question. So again, this is a sort of toy problem mainly on how to use the data in our workflow. But what we usually do for global products, we do spatial blocking. So when we train the model, we only use certain areas, and then we test in parts where we have points from other areas, and we see if we can extrapolate in these parts. But for sure, like we also try to stratify such that points that are in the same climatic regions are not repeated too much in a batch. But yeah, that's something that we usually do, but not in this small scale. But that's a good point. Okay. And let's continue a bit. So what we can also check now that we have the model is to check feature importance. And we use the split. So how many times the features make the tree split in the gradient boosting trees as a metric. And we normalize just to see what are the most important. And you can see that DTM is actually the most important feature, probably a very landforming area. In Netherlands, but it wouldn't be the case, most likely. And NDTI comes second. Then there is actually a thermal band that popped up, and EWI for water, vegetation. So you can see that row bands are not very often used, at least from the model. And yeah, now we have our model ready. What we have as a final step is to do tile predictions. And this is for another application, but it's just an example on the sort of outputs we have. This is for soil, so we also have depth, and it's also for regression. So here we have a continuous quantity while we are working now with a discrete one, but substantially we want to get several tiles, and after that we mosaic or we keep them like this, depends on what we want to do to them. But of course, you cannot predict the entire globe in only one execution. And this is the most problematic part in Colab. So I did manage to make it run, but was always crashing because it doesn't have enough RAM. So I will just, and I didn't have time to do a smaller tiles. But I did run it in our servers, and then I will show you a bit of results. But in this phase, most likely you have what you need as content is the same catalog we had before, and the mapping to between the class name to the class code, the again the tiling system, and the final model. Those are the only inputs that you need in terms of data, and for the rest, you can specify how you want to get these predictions. Normally, since we did have overlay for year, you could predict this land cover for different years. Now, to simplify, I just did it in a static way. But so I don't want to dig too much in the code itself, except the important parameters. So the way we produce our predictions, it requires an input to provide a mask. And it doesn't need, it could also be a totally full mask, but we use the geographical information of this mask also to define what's the target resolution, what's the projection. So we just copy the metadata information from this mask. And it can be, in this case, it will mask out water, ice, and desert. But this is really up to you. Again, you don't even need to mask anything out. It could be just totally full mask. And since some layers could have different resolution, we also use cubic spline. Yeah, connection dropped because indeed the RAM is probably out, but was enough to provide me the list of features. And so what we define here is, again, the catalog. But in this case, we query the catalog based on the features that were selected for the model. This means that we have at least the 30 features used from the model, but we also need dependencies on these features. So for instance, the NDVI will use the red and the NIR band. This means that the catalog will also pick, as you can see here, the row bands to derive this data. And if we have an aggregated product that is yearly, we aggregate this with the percentile, we also need the images for each single month. That's why after querying, the catalog will still have a bit more columns than what you expect. So not only the features, but also the dependencies. And now I want to go down. Yeah. And the other class that we are going to use is this tile data loader. So this class that we define will take the catalog, the mask, if we want spatial aggregation, and we don't in this case, and the sampling strategies for layers that are in different resolution or projection. And another class instead is the tile data exporter, and this is what we use to save our outputs. And again, it will automatically get the geographic informations and save, in this case, the dominant class as final output. So let me go through this. So what then the computation implies is we will loop through the tiles that we have. Here I just wanted to do one tile. So I just take the first tile, I take the tile ID. The tile ID is used to define which file will be used from the catalog. We gap fill eventual remaining gaps with the median in the tile for each variable. And we do prediction with the model we just trained. And so this is until here. And after we want to export, so this model output is probabilities, but we also want to derive the hard class through it. So we just have a method to do that and keep it in a consistent organization of the data. And then we export the hard class as byte, while the probabilities as uint16. And we want to scale the other informations consistently. So again, this phase was a bit critical, so I did it. Probably can run easily in your computer, but didn't in Colab. So I did it here for a few tiles. And so what you will have in output are folders with the corresponding tile name. And you can see inside here, I also saved some probabilities, but not all. I didn't have space for more. But I mostly saved some hard classes. So you can see this is land cover and land use for California, hard class, 30-meter resolution, on surface for this time frame. And yeah, this is global projection and the versioning. And I just uploaded it in QGIS. So let's see what we got and if it's a meaningful result. So now it's a bit confusing. Let's focus on some smaller area. So first, let's see an overview. So this is California, and it's all points, and this is the tile we just predicted. Visualization is very slow with all these points. And if we go, for instance, here, I see different classes. So